we worked on redundancy in model parallel systems. Field programmable gate arrays, or FPGAs, are efficient for running the computations required for model inference. However, some modern neural networks are too large to fit on many FPGAs. In order to run these models on these smaller FPGAs, you have to split up the computation and run different parts of it in parallel across multiple FPGAs. The problem with this is that in order to make a prediction, the results of all parts of the model that were run on all the different FPGAs are required, and in practice, some may fail or take too long to get results. One possible solution is to run each computation twice. Now, if a single FPGA fails, there was a second FPGA computing that exact same result, and we can make our prediction using this result that was computed in the other place. There are some problems with doing this, though. First, it's inefficient. For this stage, we're using twice the number of FPGAs than were strictly necessary. We also might get unlucky with failures. If two FPGAs that were running the same computation fail, now we have no way of making our prediction because there were no FPGAs that succeeded at getting this value. Another possible solution is to run the entire computation for a stage on a single FPGA. However, this limits us to the number of model parameters that fit on this one FPGA. For a large model, this is probably going to give us poor results. Our solution is to add redundancy using principles from coding theory. We add an additional multilayer perceptron, or MLP, to predict the encoding of all other FPGAs for one stage. It's not going to get the encoding completely correct all the time, but we're able to get it correct a significant portion of the time, and we believe that this solution is useful. When the FPGAs computing the direct results succeed, we just return the prediction like normal. When one of these FPGAs fail, we use the encoding value along with the computation that succeeded to recreate what this value might have been and generate a prediction this way. We can extend this idea to 3 FPGAs using 2 MLPs to predict encodings. Here, if 2 FPGAs that were computing the original values fail, we can reproduce the value of this computation using this formula here that uses these 3 results, and then we're able to take that value and reproduce what we believe the value for this first result was as well. This uses a concept from coding theory called optimal erasure codes. This basically says that we can recover k values using k results. In this case, the k values are the results of these first 3 computations, and the k values that we have are the result of this computation here, plus our 2 encoding values. We can extend this idea to larger networks by having for each stage 1 or more encoding values that are computed, and this architecture will work for any any MLP as long as the input to one FPGA only happens here and the output happens here, and you don't try to add information or take information out at any other place.